Okay, in this case we have to calculate the arc length of this curve y equal to e to the 2x, starting from the point x1 equal to 0 and all the way up to the point x2 equal to 1/2. If I consider the curve, it is an exponential, and it is something like this. It starts at x equal to 0 and it is equal to 1 here, and then it increases exponentially. We have to start at this point at x1 equal to 0 and finish our calculation at the point x2 equal to 1/2. So the curve that we want to measure the length, let's say the curve that we want to measure, the portion of the curve that we want to measure is this one in red here. So the integral of, let's say, we want to measure the length, and in order to do that we need to use a line integral, an integral of some portion of a line that I will call ds or dl or whatever you like. It's an integral over ds over this line that I can call gamma, an integral over gamma. And if we take a very small portion of this curve, let's say that this portion here is ds, which is the increment along the curve. ds is equal to the square root of, if we use the Pythagorean theorem, we have dx squared plus dy squared. So let's say that this is ds, and then if we move horizontally, this is dx, and if we move vertically, this is dy. So this is how we can express ds. So this is an integral over the square root of dx squared plus dy squared, and I can parameterize our curve. Usually this is what it's done. So we can parameterize our curve over some parameter. In this case, the parameter can also be either x or y, and I will choose x. So if I take this dx out of the square root, I can rewrite the integral like this. It's an integral over the square root of 1 plus dy over dx squared dx. And if I integrate over x, I have to integrate from 0 to 1/2. So in order to use this formula, we need to calculate the derivative of the function y, which is this one here, and y is simply the exponential above, so it's e to the 2x. And if we take the derivative of this, it is 2 times e to the 2x. So let's do it here. It's integral from 0 to 1/2 of square root of 1 plus 4 e to the 4x dx. This is the integral that we have to calculate. At this point, we can set the square root of 1 plus 4 e to the 4x equal to t. We can make a substitution. So we get that t squared is equal to 1 plus 4 e to the 4x, and from here we get t squared minus 1 over 4 equal to e to the 4x. And from here we get that x is equal to 1 over 4 natural logarithm of t squared minus 1 over 4, right? So when x is equal to 0, t will be equal to the square root of 1 plus 4, which is square root of 5, right? And when x is equal to 1/2, we get that t is equal to the square root of 1 plus 4 e squared. So this is equal to integral from 5 square root of 5 here to the square root of 1 plus 4 e squared, and then the integrand will become t times dx. What is dx? We have to find the differential from here, so dx is equal to 1 over 4 1 over t squared minus 1 over 4, 2t over 4 dt. So we can get rid of this, and here we get t divided by 2t squared minus 1 dt. So this is what we find. We have 1 over 2 integral from the square root of 5 to the square root of 1 plus 4e squared t squared divided by t squared minus 1 dt, and this is equal to 1/2. We can rewrite the integrand like this. So first let me rewrite the limits of integration. Then here we can rewrite it as 1 plus 1 over t squared minus 1. You can check that this integrand is equal to that one if you put these two terms together. And then we can also rewrite this. We can rewrite this as a over t minus 1 plus b over t plus 1. And we have to find the coefficients a and b. And in order to find them, we have to put these two terms together. So we have t squared minus 1, and here we have a times t plus 1 plus b times t minus 1. And this is just equal to a plus b times t plus a minus b divided by t squared minus 1. And in order for this to be equal to that, we have to set a plus b equal to 0 and a minus b equal to 1. So from here, we find that a is equal to minus b, and therefore minus 2b is equal to 1. So b is equal to minus 1/2, and a is equal to 1/2. Right? So here, let me rewrite it below. This is equal to 1/2 integral from the square root of 5 to the square root of 1 plus 4e squared, 1 plus 1/2 times 1 over t minus 1 minus 1/2 1 over t plus 1 dt. And finally, we can rewrite this 1/2, and then here we have the square root of 1 plus 4e squared minus the square root of 5 when we evaluate the integral of this. Then we have plus 1 over 2 natural logarithm of square root of 1 plus 4e squared minus 1, and this is divided by the square root of 5 minus 1, and then we have minus 1/2 the logarithm of square root of 1 plus 4e squared plus 1 divided by the square root of 5 plus 1. And we can also put them together a little bit more, so it's 1/2 square root of 1 plus 4e squared minus the square root of 5 plus 1/2 natural logarithm of square root of 5 plus 1 divided by the square root of 5 minus 1. And then we have minus 1/2 square root of 1 plus 4e squared, logarithm of square root of 1 plus 4e squared plus 1 divided by the square root of 1 plus 4e squared minus 1. This is just for the properties of the logarithms. And this function here is also called the inverse hyperbolic tangent of the square root of 5. And similarly, this function is the inverse hyperbolic tangent of the square root of 1 plus 4e squared